Um, so I was asked to speak about linear regression and logistic regression. So that's what I'm going to do. I don't know if it's going to be Biostat 101 or 501. We'll see how that goes. No disclosures, objectives, how to tell the difference, and then interpreting linear and logistic regression. So we'll see what we come up with. So a common use of regression is to control for confounding. So I thought I'd review or maybe new material on what causes confounding when you're doing a study. So a confounder has to be associated with the exposure you're studying. So we can think about age as often a confounder for things. Has to be cause the outcome or be a proxy measure. I'm not always sure age actually causes the outcome or if it's the processes that are along with age. And then not be an intermediate in the causal path between exposure and outcome, which is sort of a confusing one. It would be like if you're studying salt intake and risk of an MI of a heart attack, would hypertension be a confounder because it's related to salt, associated with salt intake and a cause of MI, or it would be an intermediate in the causal path if salt intake causes the hypertension, which causes the MI. So we'll ignore that one for now. So we'll see that regression takes care of the first one of these. It causes the confounder to no longer be associated with the exposure. We will see how that goes. So I thought I'd give an example of confounding, not in regression, but in a stratified analysis. So this was real data. The exposure on the rows is if somebody smoked or didn't smoke. The outcome on the columns is if they died or not. And the smokers were statistically significantly less likely to die than the non-smokers. Well, that might seem a little counterintuitive based on what we know. So the researchers stratified, which is one way to deal with confounding, on age. And within the younger age people, smokers were more likely to die than non-smokers, although not statistically significantly. And in the older people, smokers were more likely to die than non-smokers. So age was a confounder in the upper 2x2 table where we ignored age because smoking was associated with age. Most of the smokers are young. Most of them are in the less than 65 group. And smoking and age is a cause of the outcome or associated with dying. So the whole protective effect was really due to confounding by age. And when you get rid of age, you can take a weighted average of the stratum-specific relative risks, which is, in this case, a Mantel-Hansel relative risk. So adjusting for age, we get a relative risk of 1.45 for smoking and mortality, which is more along the lines of what we might expect. So that's just an extreme example of confounding. Ways to control confounding: when you design a study, you can randomize. That takes care of the relationship between the confounder and the exposure. Restriction: if you only study 57-year-old females, then age and sex can't be confounders because everybody's got the same value for those. Matching. And then in the analysis, we just saw an example of a stratified analysis. We can do multivariable analysis, which is what we're going to talk about. And we can do adjustment or standardization, which sometimes you see for vital statistics, which is sort of like a stratified analysis. I wanted to get some terminology straight because you'll hear these terms bounced around. Univariate analysis is descriptive statistics like we talked about last month, mean and medians and proportions and things. Bivariate is that 2x2 table comparing one predictor and one outcome. Sometimes you'll hear this called univariate, just to be confusing. Multivariable is having multiple predictor values and one outcome variable. Often, if you're reading a paper and they said they did multivariate analysis, what they did was multivariable analysis. So those terms get bounced around. And then in statistics, multivariate actually means more than one outcome variable. So like if you've heard of MANOVA, multivariate analysis of variance, that's more than one dependent variable. But in not statistics, multivariate often means what I'm calling multivariable. So just to get that all straight. Multivariable analysis The advantages are you can control for lots of confounders. So if I wanted to look at the relationship between smoking and mortality, and I wanted to control for age, sex, BMI, physical activity, family history of cancer, or whatever, you can only stratify so far before you start running out of people. You start getting tables with nobody in them. So that falls apart. And also, you'll notice that in that analysis, they had to dichotomize age in order to be able to stratify. They just had two categories, whereas in a regression model, which is a type of multivariable analysis, you can leave age as continuous because there could have still been residual or leftover confounding in the less than 65 age group. Maybe smokers were still younger than non-smokers. And in the 65 plus, maybe smokers were still younger than non-smokers. So there could be leftover confounding. We'll come to the disadvantages at the end. Simple linear regression, here's some more terminology. The outcome we usually call Y in statistics, I don't know why. The main independent predictor variable we'll call X. And we're going to call it simple linear regression because we only have one predictor. And this linear regression is for a continuous outcome. And we'll do an example. Oh, I can't really talk about regression without including equations. So I thought I'd better give a warning. Hopefully this is one people are familiar with. Maybe you learned this back in junior high or preschool or wherever they teach this these days. I'm not sure where. So Y is our outcome. And remember, it's some continuous variable. X is our predictor. And in regression, the predictor variable can be any kind of variable. It doesn't have to be continuous. It can be dichotomous, nominal, ordinal, or continuous. M is the slope related to X, and then B is the Y-intercept. So when X is 0, then Y is B. Another way you may have seen this, sometimes I see it written this way, Y equals A plus BX, where A is the Y-intercept. And it's confusing because now B is the slope instead of the Y-intercept. So it's just to confuse things, I think. Well, the lack of Greek letters is concerning. So another way you might see it written is the predicted value of Y, which is Y hat, equals beta 0 plus beta 1 X. Oh, I should have said X1. Well, we'll get there. So beta 0 is now the Y-intercept. Beta 1 is now the slope. Exactly the same equation, just written in statistics style. Or you might see it, the expected value of Y at a given value of X equals all that. Those are all the same. Don't panic. They're all the same. Go back to the first one if that's what you remember. So here's an example where our predictor is on the x-axis, age, and our outcome is on the y-axis, systolic blood pressure. How is age related to systolic blood pressure, or how is systolic blood pressure related to age? And we see that the regression line goes up with age. So people at higher ages on average have higher systolic blood pressure. This would be our regression model. The predicted value of systolic blood pressure at some given age is these numbers. And you use your handy statistics program to read in the data. So you can use it, pretty much any program will do this, R or Stata or SAS or SPSS. Or I was meeting with somebody yesterday who mentioned Minitab, which I hadn't heard in decades. So somebody still uses Minitab. And you get estimates of, based on these data, the best fitting line has a y-intercept of 105.7 and a slope of 0.44. So what's the slope of 0.44 mean? For every 1 year increase in age, the predicted value of systolic blood pressure increases by 0.44 millimeters of mercury. And I'll show that. I'll just write it out so we can see, because I do better if I just see the equations. Maybe other people might not, but I do. So here's just an example. I just picked a couple of ages, 59 and 60. When somebody's 59, the predicted systolic blood pressure is 131.66. When somebody's 60, with that data set, the predicted value is 132.10. The difference is 0.44, which is the slope. And that will be the same if you pick age 49 and 50 or 29 and 30 or whatever, which is one of the assumptions that the slope is the same across the range. What's the y-intercept telling us in this case? It's telling us when age is 0, the predicted systolic blood pressure is 105.7. I have no idea if that makes any sense or not. If you looked at the graph, the age range is from mid-40s up to about 80. So the lesson is, don't extrapolate beyond your data. It's not usually a good idea. Here we have number of husbands yesterday, 0, today 1. Next month you'll have over 4 dozen husbands. Don't just let's stick to our range of our data set. So the y-intercept doesn't always have a meaning. Let's make it more complicated. So multivariable, sometimes you call it multiple or multivariate linear regression. You add more x's, so you can add more predictors to your model. Same model, we've just added some predictors. And when you do this, well, I'll do an example. So let's add BMI. So when we do this, I didn't draw the picture. I stole this from some statistics book, and they didn't have a picture of the three-dimensional adding BMI. Beta 1 is the slope for age adjusted for BMI, and beta 2 is the slope for BMI adjusted for age, for confounding by the other variable. And I'll show you how that works in a minute. Actually, I will show you when we get to logistic regression. Assumptions of linear regression. I learned this mnemonic somewhere along the line, so somehow that's the one I can actually remember. Linear relationship between x and y if x is a continuous variable. That's the assumption that the slope is 0.44, no matter what 1 year age increase you look at along the range. If x is dichotomous or nominal or ordinal, you don't have to worry about that. Independent observations means each point in that graph was a different person. It's not like you measured the same person at age 40 and 50 and 60 and 70. Otherwise, as I think Dr. Taylor talked about last month, there are models, like multi-level models, where you can account for that, but we won't go there. Normal distribution of the outcome, actually it's of the residual, but we'll go with the outcome at each value of x and equal variance of the outcome at each value of x. Well, that works well for most continuous variables. And even if there's not a normal distribution, it usually works due to the central limit theorem, usually works if your sample size is even. But it doesn't work at all if your outcome is dichotomous. You can't use linear regression because it doesn't meet these assumptions. So for dichotomous outcomes, we'll jump over to logistic regression. Here's the equation. It's almost exactly the same. So here's one with 2 predictor values. The right side is exactly the same. The left side, instead of having it be y equals all of that, it's the natural log of the odds of y. It's just a different function. And that works for dichotomous predictors, whereas just having y equals all that doesn't work for dichotomous predictors. And a reason the logistic regression is popular is that the slope can be interpreted as the log of the odds ratio. So if your predictor is dichotomous and we define exposed as a 1 and not exposed as a 0, beta 1 will give us the odds ratio, the log of the odds ratio for the exposed compared to the unexposed. Oh, another reason logistic regression is popular is because it's about the only regression model you can really use if you're doing a case control study. It works for case control, whereas any of the other regression models I'm going to mention don't. So for the 2 of you who might care, I thought I'd show you how the logistic regression model ends up being the log of the odds ratio. So here we go. If you don't care, well, here we go anyway. Sorry. So the log of the odds ratio is the log of the odds of the outcome in the exposed group divided by the odds of the outcome in the unexposed group. And as you also remember from junior high, the log of the ratio is the difference in the logs. Okay, good, just nod. So then we can substitute our equation in right here, because it's the log of the odds in the exposed group minus the log of the odds in the unexposed group, which simplifies to beta 1, which is what we have up here. So here's the amazing thing. If x2 is the same in both of these, then beta 2 x2 minus beta 2 x2 falls out, which is how we ended up with just beta 1. If x2 is, say, age, if age is 50 here and age is 50 here, beta 2 x2 falls out. And if age is 50 here and age is 50 here, age can't be a confounder because everybody has the same age. You've held age constant doing that. Or if age is 60 or if age is 20, whatever it is, you've held it. If you hold it constant, then you're getting the slope for x1 adjusted, holding x2 constant. If x2 is the same, it falls out, and this beta 1 is adjusted for x2. It's like stratifying on every possible value of x2. It's holding it constant. So I'm looking to see looks of amazement. It's amazing. It's amazing. So I'll do an example from a statistics book where they were looking at the outcome is having an MI. This was a prospective cohort study. The predictor value was dichotomous. It was if you're a type A behavior or type B, what's type A is like high strung, stressed, whatever, maybe all of us. Type B is more the laid back, relaxed, whatever. So they want the log of the odds. So they've got yes as a 1 and no as a 0, which is the easiest way to code things by behavior type. Give the data to whatever program you like to use. We got a y-intercept of negative 2.93 and a beta 1 of 0.86, which I'm just showing if you plug in the numbers, that solves to 0.86, which is better because that's how it works. And then if you exponentiate, you get the actual odds ratio. So the 0.86 is the log of the odds ratio, but just remember that. So if we exponentiate, it's back to odds ratio. Some statistical programs, like SAS, will give you both the coefficient. We'll call the 0.86 the coefficient. So the slope in a model, it can be the slope or the coefficient or the parameter. You might hear it called any of those things. SAS will give you that and the odds ratio. Stata just gives the odds ratio unless you specifically ask for that. So it depends on the program. So we're saying that type A behaviors, the odds of having an MI was 2.37 times higher than the type B behavior people. Well, what if we want to adjust for smoking? Maybe we know smoking is a cause of MI, and smoking may be related to behavior type. We can add smoking to our model. Run it through the program. Now our beta 1 is 0.83 and our beta 2 for smoking is 0.59. The odds ratio for behavior type from this model is that, which is 0.230. And the odds ratio for smoking, if we do exponentially that, is 1.80. So we can see smoking really wasn't much of a confounder because on the previous, when we didn't adjust for smoking, the odds ratio was 2.37. Now it's 2.30. That's not really enough to change your interpretation. The guideline for if something causes confounding is, did it change enough that it changes your interpretation? And 2.30, 2.37, that doesn't really do it. If people don't want to think too much, then what they do is just say, did it change it by more than 10%? If so, we'll call it confounding. If not, but you're allowed to think about it too. So that's logistic regression. So we did linear and logistic. I wanted to briefly mention a couple of other models that you might run across, or maybe 3 other models. How are we doing? Oh, good. Proportional hazards regression, or Cox regression, you may hear about for time to event outcome. So it's generally called survival analysis. So time to survival time, so time to death is traditionally what it is, but it can be survival to a good outcome too. I've worked on smoking cessation studies where it's time to quit smoking. Then it's a good thing to have a short time, but it's still called survival analysis. Almost the same model. The right side still pretty much the same. The left side, instead of y or the log of the odds of y, is now the log of the incidence rate of the outcome. And the y-intercept changed a little bit where it can vary depending on follow-up time. The nice thing about proportional hazards models is you get something you can interpret just like a logistic regression model, where here the slope is the log of the hazard ratio for the exposed compared to the unexposed, adjusted for whatever else is in the model. And the hazard ratio is basically the average relative risk across follow-up time for survival analysis. So you can really interpret it like it's a relative risk. So that's a popular model you might run into. For count data, I think last time Dr. Taylor mentioned Poisson regression for count data, where you can get relative risks out, adjusted relative risk from that. And negative binomial regression is similar to that. So those are other ones you might hear about. Those are probably all the most popular regression models, I think. Well, I gave the benefits of multivariable analysis. What's the downside? One is, I didn't give the assumptions for logistic regression. So logistic regression, once again, independent observations, otherwise you have to switch to a more complicated model. The outcome follows a binomial distribution, which if it's dichotomous and they're two mutually exclusive values, it does follow a binomial distribution, so that's easy to do. And if it's a continuous predictor, then it follows a logistic relationship among the range. So if it's age, you're saying that's the same odds ratio as you go from one age to the next age. Statistician George Box is famous for saying all models are wrong, but some are useful. So you're never going to meet the assumptions exactly, but hopefully you're close enough. The other downside is that, to me, and there's at least one epidemiology book by Rothman, I remember, he suggested, don't ever do a regression model without first doing a stratified analysis so you can actually see the data. When I've got 2x2 tables, I can see what's going on. When I throw everything into a regression model, I can't see what's going on. This was weighed in kilograms from a data set I had on people who underwent vascular surgery, and I've just shown the first few and the last few. I skipped the middle 96%. So these are people who underwent vascular surgery. I'm guessing somebody didn't weigh 1 kilogram, just a guess. I'm guessing people didn't weigh 622, 700, 888, or 999 kilograms. If you put this into your regression model, the program will be happy to treat those as valid values. It doesn't know any better. 999 is often used as a missing value code, so that's probably why there's 26 of those. 888 is often used as not applicable. I don't know why weight would be not applicable. I don't want to think about that. 622 and 700 just look like errors. If I get a data set like this, first of all, I'm not going to do regression until I've looked at this, at the data. And then if you can go back in the records and find out what they were supposed to be, that's great. If you can't, what I do is change them to missing. That's my rule of thumb. So look at the data before you analyze it. And don't just jump right into regression analysis because you'll miss things like that. I'm filling out a reader survey for Chewing magazine. They asked how much money I spend on gum each week, so I wrote $500. I said I'm 43 and my favorite flavor is garlic curry. I love messing with data. So don't look at the data first so Calvin won't have messed up your data. I guess that's the lesson. Oh, that was it. I can stop sharing. That worked. Any questions?
Thank you, Peter. I used a lot of regression approaches during my PhD training, and I commend you for being able to put it in a presentation that is, at least somewhat followable, because every time I tried to explain it, I always had trouble. Does anybody have a burning question that they want to start us off with?
Maria does.
Quick question. I apologize if I missed it. Is that for logistic regression, do all of the kind of the variables that you're trying to account for, do they also have to be dichotomous, or can they be?
So I think I mentioned it for linear, but not logistic. The predictors for any regression model can be anything.
Okay, thanks.
And if they're continuous, they don't have to be normally distributed.
Okay, thanks.
Yeah, thanks I didn't bring that up for logistic.
I have a question. So I know that each, regression model has its own specific uses based on your data structure. If we forget what we learned today, do you have any favorite either online or, other resources that you would recommend to kind of look at what, figure out what regression approach might be the best for the question that we're trying to ask?
Um, Not website. I mean, I have a favorite book that covers linear, logistic, and proportional hazard regression. I don't know, which I've used in a class before. It's called, I don't know if that's readable, Regression Methods in Biostatistics. Is that what it says? Second
Yeah.
edition. And it's about as readable as you're going to get on the topic. They use Stata throughout. I don't remember if their website has codes, and it's by Wittinghoff et al. Out of UC San Francisco. It focuses on linear, logistic, and proportional hazards regression, but it talks about other models too. It brings up, has a chapter on multi-level models if you don't have independent data and things like that. So that's my favorite. Am I allowed to have a favorite statistic book? That's my favorite statistic book.
Sure, thanks.
Peter, you're allowed to have a favorite statistic.
Oh, okay.
And I love the fact that it's within arm reach.
Yeah. Yeah, I've used it for class, but I also use it to look things up that I'm like, what are restricted cubic splines again? Let me see what they said about that kind of thing. So they cover a lot of that. And they have a website with their Stata code for what they did. So sometimes, although I usually use SAS, sometimes I jump to Stata just because that's what they're using.
Other questions?
I have a question. I don't know if it's relevant to this. So a lot of time, I have a trouble to figure out if I should use, the regression model with the multiple factors, or I should just try individual factors, do the linear test first before I do that, and then including any potential interactions in the model.
Yeah.
And then if I do individually, do I have to adjust my p-value depending on how many factors I want to look at it?
Yeah, good question. And actually, you're reminding me, I didn't really talk about other uses of regression besides controlling for confounding. So one is you can include interaction terms to look for interactions. So if you don't want to assume the relationship between age and systolic blood pressure is linear, you can include an interaction term that might allow it to be different. Another use is to build prediction models, which is a little more complicated topic. So I always start with unadjusted because I want to see what happens when I put variables in. If I have like 5 potential confounders, I'm probably going to add them one at a time first, just to see how each one affects the main predictor of interest, and then maybe put them all in. If I'm really looking at confounding, I don't worry about the p-value because really it's how much does the estimate change? Does it change by more than 10% or not? It's not what the p-value does. Also, I don't know if there's strong arguments in the epidemiology world about, in most situations, not adjusting for multiple comparisons. But I have like a stock paragraph I use when a reviewer says, you did 10 comparisons and didn't adjust. And it's like, yeah, because they were 10 independent comparisons. They weren't like pairwise comparisons after an ANOVA. They were separate comparisons, so you judge each one on its own. Anyway, there's some interesting arguments about that. Does that sort of answer?
Yes, yeah. Thank you.
Any additional questions for Peter? And if not, Yvette, I will hand off to you for introductions for our didactic, and before Meredith reminds me, I will pause recording.
Right.